So I'm asking actually the question that not many people are asking, which is basically, can existing mass transfer techniques handle fabrication variabilities in micro LEDs? Micro LEDs are semiconductor devices, and as such, you expect to see that those devices will suffer from variabilities. Whether variabilities that are within wafer or within lot, or maybe lot to lot, or even tool to tool. And all these variabilities, the microtransfer technology, and I'm talking here about deterministic mass transfer in particular. I'm not talking about all mass transfer techniques, but my focus is on deterministic ones. The rule of thumb in semiconductor high volume manufacturing is that any process must be tolerant to variabilities of about 10% plus or minus 3 sigma. And when I pose that condition and project it onto electrostatic MEMS transfer techniques, for example, or elastometric stamp techniques, PDMS techniques, I'll find that these techniques are incapable of maintaining HVM line due to the incompatibility with variabilities. For example, the electrostatic MEMS technique. If you have any non-flat surfaces or any gap between the electrostatic head and your micro LED, that actually creates, that gap would require higher voltage. You apply higher voltage, you may actually damage the micro LED, and so forth and so on. And for elastometric stamps, the same problem does exist. And I'll talk more about what kind of other issues we have there. So this is really the motivation for us. If you look at what are the elements for a manufacturable deterministic transfer, our previous speaker talked generally about yield, throughput, cost, performance, and I am actually adding into this is the maybe it comes under the performance, which basically the day-to-day operations for the assembly process engineer, standing on the assembly floor. Is the stamp tolerant to variabilities in my coming micro LEDs? I like to have that greater than 3 sigma of the height or the dimension. Is the stamp tolerant to misalignment, for example? Is the stamp scalable? How big, how small? What kind of cost issues are related to this? We know that simple things are more manufacturable than more complex things. So what is the cost of the stamp? Does the use of this particular transfer technique require certain customization for the micro LEDs? And if you require more and more of the customization levels, then that also adds to your cost quite a bit. And also there is, of course, the throughput and the fidelity and the yield, of course. So I'll talk to you about an electromagnetic pattern-sensitive head technique that Luxnour invented. I'll explain the principle of operation and how that actually works, then move on to describing the transfer process based on that PSH. Then I will dig deeper into the manufacturability attributes of the pattern-sensitive head before I conclude my talk. So this is an image, actual image of the pattern-sensitive head, the PSH. And at first sight, what strikes you when you look at this image is, its simplicity. There's nothing here other than lines of this continuous high magnetic permeability material. In this case, I added nickel. That is embedded in non-magnetic material or dimagnetic material. This is it, nothing else. There are no moving parts, there are no MEMS. You don't pass current, you don't pass voltage. This is all that you see. So that simplicity actually is very striking, and it will come very handy in terms of the manufacturability attributes of the technique. So what would happen when if you have a magnetic field, that is actually parallel to these nickel lines or the high magnetic permeability lines. If you focus on the magnetic field direction before you embed, the PSH, you'll find that the magnetic field lines are all straight and they are actually parallel to the direction, that you